Okay, applications of exponential and logarithmic equations. And I'm going to start you off with reminding you of some formulas and showing you a couple of new formulas. So, first of all, let's take a look at some growth and decay formulas. So, one formula that we have looks like this. And let's define these variables. A is the total amount of what we have, and A with a little zero down here is the initial amount, or the starting amount of what we have. So maybe it's bacteria. So the total amount of bacteria we have, well, we start off with an initial amount, and then X is known as the growth or the decay rate. So X bigger than 1 means that it's growing, and X smaller than 1 means it's decaying. And we won't have a base X equal to 1 because it would be really boring. It would not do anything. It wouldn't be growing or decaying. So some examples of that is a half-life, X would be 0.5, or if you had bacteria doubling or a population doubling over time, the X would be 2. Increasing by 5%, that would be 1 plus 0.05 or a 1.05 X value. Decreasing by 20%, that would be a 0.8 X value, and so on. T is the time, and capital T is also the time, but it's a special time. It's the growth or the decay time. So it's like how long is each growth period or how long is each decay period. For instance, if it's a half-life of every 10,000 years, this capital T would be 10,000. Now there's another type of growth that we'll talk about in this unit, and that's continuous growth. So this first type of growth is at a rate that is happening every period. So every month or every year, every second, every 10,000 years. But there are some situations, really like bacteria or compound interest in banks, where the item is growing or decaying continuously. And for that, we use a bit of a different equation. We use a formula. It still has many of the same elements. So A is still the total amount and A0 is still the initial amount. But now we use a new base, and that base is called E. And E is a constant, kind of like pi. It's a transcendental number, and it's approximately equal to 2.71828, but it goes on forever. And it is on your calculator. It is a small e right below the pi symbol on the TI-83, TI-84. So see if you can find that. And this e is then raised to what we call K and T. So T is not a problem, T is the time, but K is a new number. It's called the proportional growth constant. So K is really relating at what rate is this thing growing. And we'll take a look at some of these examples either in the notes today or in class. Okay, there are two other formulas similar to these that are the compound interest formulas if we're dealing with money. So let's just list those out as well. And the first one is A equals P 1 plus R over N to the NT. So a number of these terms are the same as the definitions that we had before. A is the total amount. P is the principal, or you can think about that as the initial amount, A0. R is the interest rate, and that's generally per year, so 3% per year or 10% per year. N is the number of compounding periods. So N is the number of times we cut our rate up, and it's also the number of times we apply the rate. So, for instance, if I am dealing with years, so like a 3% increase per year, I'm dealing with 1.003 divided by 1, and so that's just equal to 1.03. So you're increasing by 3%, 103%. And then you're doing that one time times the number of years. Whereas if I do this in months, I cut this up. So now this is 12. And so 0.03 gets divided by 12, and I get a smaller number in here, but I get a much larger number here because every year, so if t is in years, every year I have 12 compounding. So I'm doing smaller compounding, but I'm doing it way more often. And that will result in a different number than compounding once a year. And it actually is much better if you are an investor to have more compounding periods if it's the same rate. So if they're offering me 3% per year, and I say, well, can I get it compounded monthly? And I will get more money that way. It won't be a ton, but I'll get some more money that way. And if I can convince them to do compounded daily, I'll get even more money. And if I could convince them to do it secondly, I would get even more money. And that leads us to the next formula, which is, well, what happens if I could convince them to give me continuous growth at a very, very, very small rate? And they actually do that, and this is what the formula looks like. A equals P, and here's our favorite number, E, and now it's just to the RT. And that rate is the interest rate per year. So if you do 3%, it's 0.03 as that constant term in front of the t. So let's take a look at a few examples using these, and it should make a little more sense for you. So let's do a non-finance one first. At what depth does a diver encounter only 2% of the normal amount of light if they lose 10% of the total light each meter they go below the surface? And just to be clear, by total light, I mean if you've got a diver and they're at the surface, they have 100% of light, and then once they go down 1 meter, then they're at 90% of light. But when they go down another meter, they lose 10% of 90. So they don't go down to 80, they're at 81% of light. And then when they go down another meter, they lose 10% of 81, and so they lose 8.1, and they're at 72.9% of light. Now, I'm not sure if this is actually accurate, but let's take a look and see if these were the conditions, how deep this diver would go so that they would only have 2% of sunlight reaching them. Okay, let's start by creating a formula for this, and that will be A equals A0, and then I'll use the X formula and T over big capital T like this. And A is the total amount that I'm going to get to. So in this case, that's like 2 or 2%. Starting amount of light that I had was 100%. So I'm starting at 100 and I'm going to go all the way down until I get to 2%. And my rate is a decay rate, so I should have a number less than 1. And what's happening here is I'm losing 10%. So that's 0.9. And how often I'm losing it isn't really time, it's distance or depth. So I'm losing it every meter that I go down. Now, if I went down and I was losing it at 10% every 5 meters, then I would have to divide this by 5. Really, I'm dividing it by 1. So that capital T value is how long it would take, in this case, for light to go down 10%, and that's each 1 meter. So per 1. I won't write that down. So now I get, I'm just simplifying this a little, I get it to look like this, and now I have to go solve this. And to solve for an exponent is going to require us to either use guess and check, graphing, or logs, and I would like you to use logs to do this. I divide out the number that's in front rather than start logging right away. So if I divide both sides by 100, I end up with 0.02 is equal to 0.9 to some power. And now I log, and I can log any base I want. So since my calculator can do lons and my calculator can do log base 10, I'm going to use log base 10. So 0.02, and I'm going to log the other side, log 0.9 to the power of d. Create myself a little room here. Log 0.02 is equal to d log 0.9. So I use the log rules to bring the d down. And now I solve for d. So I divide both sides. Log 0.02 gets divided by log 0.9. And grab your calculator and see what you get. It's about 37.13 meters and approximately 110 feet down below the ocean surface in this case. I'm probably off with some of my stats here, but the application and the math behind the application is all correct. So let's take a look at a financing one, and I'm going to break it into a few parts just so you can see the difference between some different approaches for this next example.